All right, I'm sure you all are really starting to hate me because I keep telling you that it's over or almost over, and then I keep thinking of something else. We went over this in class, but for those folks who were not in class this day, I do want to give you a quick podcast view of the adaptations to photosynthesis that we talked about. So that's what we're going to get ready and do. Okay, adaptations to photosynthesis. Now, what we are talking about is essentially the main problem that plants have is what happens when there's no water, when we have a drought. Okay? We've talked at length about stomata and how they operate, that if in times of drought, they will close so that the water that is in the plant will not just evaporate away. That's a good thing. The bad news is that the plant can't get any CO2, and without CO2, we cannot build sugar molecules. We cannot do photosynthesis. So plants in drought situations then are under serious stress. In addition to that, okay, the threat of water loss versus not getting CO2 in, there is an additional very serious problem that some plants have overcome while others have not. The type of photosynthesis we have talked about when we learned about what photosynthesis was, the light reactions and the Calvin cycle and all that, is called C3 photosynthesis. And I want you to think of C3 photosynthesis as being normal. This is normal photosynthesis. No doubt it is the first of the pathways of the photosynthetic adaptations that evolved, just normal photosynthesis. It is referred to as C3 because the first compound that's made here in the Calvin cycle is a 3-carbon compound. You really do not need to remember that. I'm just telling you what the name is based on. Okay? But the problem with this type of photosynthesis is that it all hinges on the ability of rubisco. Here, remember what I'm showing you right now is the Calvin cycle. And this is the part that happens in the stroma of the chloroplast, as we've talked about. So this is after the light reactions have happened. We have a bunch of energy in the form of ATP and NADPH to use. This is where we're going to use it. The success of the Calvin cycle entirely hinges on the ability of this enzyme, rubisco, to do its job. And if you'll remember, the job of rubisco is to grab CO2 from the atmosphere, okay, and nail it down to a big old carbon compound we see here called rubip, okay? And that is called carbon fixation. Okay? And when the carbon is fixed, when that CO2 is nailed down to the rubip, then we proceed on through the Calvin cycle with our goal to make sugar. However, we have a problem. Rubisco is stupid. He cannot tell two things apart that he really, really does need to be able to tell apart. He cannot tell apart CO2 from oxygen gas, okay? And this becomes a particular problem in a drought situation because if the stomata are closed, CO2 levels in the leaf are going to go down because our source for CO2 is the atmosphere. And if we close our stomata with the guard cells, then the CO2 cannot get in the leaf. So the plant will use whatever CO2 is there, and the amount of CO2 in the leaf is simply going to decrease as it is used. Now, conversely, the amount of O2 in the leaf is going to rise. Why? Because, of course, as I know you remember, the photosynthetic equation tells us that if we have the light and the CO2 and the water, and we are going to get glucose, and we are also going to get oxygen being produced. So this level is going to go up in the leaf, again, because our stomata are closed and we're not going to let it escape into the atmosphere like we should. When the amounts of oxygen in the leaf are high and the amounts of CO2 are low, Rubisco is just as likely to grab O2 out of the air and stick it onto rubip as it is CO2. That is a huge problem, because what happens is we make carbon compounds when we do that that are completely unusable by the plant. They get expelled from the plant, and so the plant is just giving off huge amounts of carbon as a waste product. That's bad, and that leads to plant death in the time of drought because we are using so many resources in a wasteful way. This process is a very important word. I've seen it pop up on the AP exam. Is called photorespiration. Okay, and it is bad with a capital B-A-D. Okay, so photorespiration is this act of Rubisco grabbing oxygen instead of CO2 from the atmosphere and sticking it onto rubip. And it does so because in a time of drought, O2 will be building up in those closed off leaves while CO2 will be decreasing as it's being used. Okay, and Rubisco can't tell them apart. Now, what we're going to talk about next is two different ways photosynthesis has been adapted by different groups of plants to deal with this situation, to deal with this photorespiration problem. Okay? All right. The first way is called C4 photosynthesis. And in C4 photosynthesis, the cells in the leaf themselves have been modified. In other words, we have new cells that are designed to deal with this problem. And the cells that we have that are new are these. These are called bundle sheath cells, and you should be able to recognize that term. This is a regular mesophyll cell that we saw hanging from the model in class. It's where all the chloroplasts are. That's where photosynthesis happens. So a typical mesophyll palisade layer cell, this is where the photosynthesis is happening. And normally the Calvin cycle would be going on in the chloroplasts up here along with the light reactions and so on. But in C4 photosynthesis, we have added another cell, and it is heavily, heavily, heavily protected. Not just any stuff can diffuse into this, okay? And what we do in this cell is we tuck away the chemicals of the Calvin cycle. We put the Calvin cycle down here, which means we put Rubisco down here, where it is protected. It is never, ever going to bump into oxygen. There will be no oxygen allowed in this bundle sheath cell. I don't care how much oxygen builds up everywhere else in the leaf. It can be all over the place in this leaf. We are not going to let it in here. If you'll take that. We're not going to let it build up in this cell. It will not be allowed. So that means Rubisco can live in here and do its job. But how does it get the CO2? There is another enzyme up in the mesophyll called PEP carboxylase. PEP carboxylase went to college. He knows how to tell O2 from CO2. And I don't care how much O2 builds up in the cell, PEP carboxylase will never ever reach for it. It's always going to grab whatever CO2 is present. So it will grab CO2, stick it onto another carbon compound, and then that will be shipped down here. The CO2 will be released, and then Rubisco can grab it and doesn't have to worry about trying to distinguish it from oxygen, because we're not going to let oxygen be there. So C4 is an anatomical adaptation. It is an anatomical adaptation, okay? That's one way to deal with drought. Here is the other, CAM photosynthesis, and this is a this is chemistry based, or a chemical name. CAM is short for something that is a much longer term, and we don't care what it stands for. Now, what's different about CAM plants is simply this is a temporal solution, meaning a timing. This is all about the timing. All right. Day versus night. Okay? During the day, if you have dry conditions, they are going to be at their worst during the day because of the heat of the sun. So this is when we are going to close our stomata. CAM plants will close their stomata during the day, but at night, when it's not so bad as far in terms of water loss from the plant, we are going to open the stomata. And CO2 is going to be allowed to come into the leaf during the night. Okay? So what will happen is at nighttime, the stomata open, the CO2 comes in. Okay? Now, when the CO2 comes in at night, we can't use the CO2 at night. We can't use it. We can collect it, but we can't use it. Why can't we use it? Because we need the energy from the light reactions. We need the energy from the light reactions, and those cannot occur at night. So we have to store the CO2. We have to collect it and store it. We store it in the form of an organic acid, and the acid is what this is named for. And then during the day, we take the CO2 out of storage and feed it to the Calvin cycle that is allowed to run with photosynthesis, the light reactions during the day. Okay? So we store it at night, we use it during the day. Simple solution. Elegant, simple, powerful. Okay? Believe CAM plants are things like cactus. I often get the C4 and the CAM flipped around in my head, but C4 CAM adaptations we're going to find in desert or other dry places, maybe in class I'll try to pull together a little list so we can kind of get a picture in our minds of which plants would be which. All right. This is just a side-by-side comparison. Again, this is the C4 and this is CAM. Oh, it was already written, sorry. This is showing you have a physical separation of the Calvin cycle, and here we're just taking in our CO2 at night and we're using it during the day. Okay? All right. That's what we talked about the other day when several people were out. So I hope that makes sense. If it doesn't, let me know and we'll talk about it. Thanks for watching. Take care.